Today we'll be talking about the shape of molecules. Our lesson standards is that we'll use the periodic table and electronegativity differences of elements to predict the type of bonds that are formed and write the names of those chemical compounds, including polyatomic ions, using the IUPAC criteria. Then we'll use Lewis dot structures and electronegativity differences to predict the polarities of simple molecules. We'll construct an argument to explain how electronegativity affects the polarity of basic chemical molecules. Our lesson objectives. We'll name a few of these here. Well, given the name and molecular formula of covalent molecules, students will be able to predict and name the structural formulas for simple molecules 8 out of 10 times. Given the number of electron groups and lone pairs around a central atom, students will be able to predict the molecular shape 8 out of 10 times, and given the electronegativity values, students will be able to predict the molecule's polarity 3 out of 5 times. So at this point in the lesson, I asked students to chime in on what they think would cause a molecule to be one shape or another. There's a lot of different responses to this during class. A lot of students pointed out that they think it had something to do with the electrons. All right, so before we get started, we'll do a quick vocabulary review. Our main thing that we're going to be looking at today is electron groups. So when we say an electron group, we're saying anything that is a grouping of electrons. Most often this is a bond, either a single, double, or triple bond. It can also be a lone pair or a single electron. So when we're talking about a bonded pair, we're looking at a Lewis dot diagram there below. We mean any electrons that are found in a single or double or even triple bond. And no matter how many electrons are in that bonded pair, it's still considered to be one group. So a single bond is an electron group, a double bond is one electron group, and a triple bond is also still one electron group. A lone pair are electrons that are not bonded but are found only on one atom. So that illustration to the right points out some of the lone pairs existing on ammonium. We've got on the nitrogen there in the center, and then also some on sulfur dioxide. The oxygens and sulfur each have a lone pair, at least one lone pair on them. So then we went ahead and practiced using this terminology. So I asked, how many electron groups does carbon have in methane? So we've got a picture of methane on the right, and how many electron groups does it have? And carbon does have 4 electron groups in methane, and those are now circled, each with kind of a square there actually. So each one of those is a single bond representing 1 electron group. So carbon, the atom in the center of the molecule, has 4 electron groups. Next we'll look at sulfur dioxide. So sulfur dioxide pictured here. We want to see how many electron groups does sulfur have in this atom. And sulfur dioxide has 3. This was a bit trickier. So you have to remember that both lone pairs and bonded pairs are considered electron groups. So sulfur has 2 double bonds. Each of those is an electron group, and the lone pair on sulfur is also an electron group. So it's got a total of 3 electron groups. So we're going to use this information about electron groups to now answer that fundamental question we asked at the beginning of class. Why do molecules make shapes? And the short answer to that is that electron groups, ones we just looked at, those bonded pairs, those lone pairs, are going to repel, aka push away, other electron groups. I asked students to think about why this would happen. So what do we already know about electrons that would cause them to repel other electrons? Most students remembered that electrons do have a negative charge, and just like a magnet, like charges are going to repel. So opposite charges would attract, but like charges are going to repel. So electrons, because they have that negative charge, are going to push other electrons away. And so our shapes are going to form based on this kind of textbook definition here, that the preferred geometry of a molecule is the one in which the electron groups have the maximum separation, which therefore is the minimum energy possible. There's a section in the song that I've been playing, The Shape of You, in which it says, I'm in love with the shape of you. We push and pull like a magnet do. And that's exactly what's happening in these molecules too. They're pushing and pulling like a magnet to form these shapes. There's varying levels of repulsion though. among these groups of electrons. So our most repulsive, this is going to be the ones that push the other electron groups away the most aggressively, are going to be between a lone pair and another lone pair. They really don't want to be next to each other. Then the next most repulsive will be a lone pair to a bonding pair. So a lone pair would push a bonding pair away. And then our least repulsive would be a bonding pair to bonding pair. So even though they still don't want to be next to each other, they're not going to push each other away as aggressively as an electron group that has a lone pair involved in it. So everything that I've just been describing up to this point is called VSEPR theory. And when I hear the word VSEPR, I always think of this character here to the right. She's in Casino Royale, a movie with James Bond, and her name is VSEPR. So we're not talking about her. Instead, I'll give you the abbreviation for what VSEPR does stand for. So VSEPR instead stands for valence shell electron pair repulsion. I think we know what all those words mean separately, but let's look at them again and then we'll put them all back together. So we've talked about valence shell electrons for a few weeks now, and we know that valence shell refers to those electrons that are in our outermost energy level. And those are the ones that are going to be important for bonding because they can either be transferred for ionic or shared for covalent. An electron pair is just like it sounds. It's a pair of electrons. And we talked about at the beginning of class today, those can be a lone pair or a bonded pair. And then finally, repulsion. So that is the act of like charges pushing other like charges away. So now that we know what all those things mean together, we can put it all back together for our valence shell electron pair repulsion. So essentially we're saying that the electron pairs that are located in our valence shell are repelling each other. And that's what we just talked about is what's going to make a shape. So when you search for VSEPR theory, often what's going to come up is this image I'm going to show you next. It's essentially just a listing of those different shapes. It's pretty much synonymous. If you're saying VSEPR, you mean what shape does that molecule make? So this image here is going to be your best friend as you do your homework for this week. It lists the molecular shape that these different molecules can make, and it's going to be based upon the number of electron groups, which we were finding earlier today during class, and the number of lone pairs. So we were looking at kind of both of those things, and those together are going to determine the exact shape that this molecule makes. So again, our molecular geometry is going to depend on that number of electron groups around the central atom, and then how many of those are bonded versus lone pairs. So those are the two questions that I'm going to be asking you over and over again throughout this lesson is how many electron groups are on the central atom, and how many of those are lone pairs. All right, so most of the rest of class, you're going to be determining the molecular shape of a few of these atoms. So you're going to do the following 3 steps. We're going to do them together here. So first, we're going to draw the molecule following our Lewis dot diagrams that we used previously to create that molecular structure. Then we're going to notate the number of electron groups and number of lone pairs around the central atom. And finally, you're going to use this information and the VSEPR chart to determine its shape. All right, so let's go ahead and get started and practice a few. So the first one that I had students draw was methane. So methane, we're going to go ahead and put carbon in the center, and we're going to put hydrogen on each of the 4 sides. Before we start drawing, I do want to notate the valence electrons. So carbon has 4, hydrogen each have 1, so it's going to be a total of 8. We're going to add those valence electrons. Again, hydrogen each having 1, and then I'll put carbons in a slightly different color. Carbons have 4. And then we can just make those bonds between our electrons. So we've got a bond here between carbon's electron and hydrogens, and that's just going to repeat on every one. So we're going to have 4 single bonds between carbon and hydrogen. So now we want to know how many electron groups does carbon have. And so if we look at this molecule again, we know that every lone or bonded pair is an electron group. And so carbon has 4 electron groups in this picture. And does carbon have any lone pairs? Nope, I don't see any. Carbon has 0 lone pairs. So now we're going to use this chart to find out what shape does carbon bonded with 4 hydrogens, which we do call methane, make. So what shape does methane make? So we're going to look here for the number of electron groups, and we're going to go down to the one that says 4. And then we're going to go across to find the one that matches with 0 lone pairs. And 0 lone pairs is up here. So we're going to find where those intersect. And that's going to be right here. So it's a tetrahedral shaped molecule. So our tetrahedral shaped molecule will have no lone pairs, 4 bonded pairs, so a total of 4 electron groups. It's going to kind of look like the image there, and it is going to have exact bond angles between them. So each of those electron pairs, because it's the same type, it's all bonded pairs, they're all going to push at the same kind of repulsion level and to be farthest away from each other. So that bond angle is going to be 109.5 degrees so that they can each have the maximum separation possible. All right, the next one we're going to look at is aluminum bonded with 3 chlorines. We'll call this aluminum trichloride. So aluminum is going to have 3 valence electrons, and chlorine each have 7. So that's going to be a total of 24 valence electrons. So we're going to put aluminum in the center. So there's one of it, and then we have 3 chlorines. So we're going to kind of put those around them. And we'll indicate our valence electrons. We know that chlorine each have 7. So that means when we draw the Lewis dot structure, 3 of the sides will have 2 and 1 side will have 1 valence electron. Aluminum has 3 valence electrons. I'm going to just go ahead and put those in blue. So we're going to add their 3 valence electrons around aluminum. And now we can kind of see what's going to happen is we've got those single electrons on chlorine, and they're going to bond with one of the ones on aluminum. So we're just going to make 3 single bonds here to create our structure, aluminum trichloride. So now, how many electron groups does aluminum have? So we know electron groups are bonded pairs or lone pairs. So we've got 3 here on aluminum. Again, we're only looking at the central atom to determine its molecular shape. Oop, I just wrote aluminum there, so sorry. 3 is our answer. 3 electron groups. So now how many lone pairs does aluminum have? So even though chlorine's got some lone pairs on it, we're only concerned about the ones on aluminum. And we don't see any lone pairs on aluminum. So this one's also 0. All right, so now we're going to find out what shape does aluminum trichloride make. So we have to find the one that's got 3 electron groups. So we're going to go to the one with 3 electron groups. And then we're going to find the one that also has no lone pairs. So that's marked right here. Trigonal planar is our shape. And trigonal planar, just like the name suggests, it's pretty much a triangle that's in a plane. So in a plane, that means that it's flat. It's a flat molecule. It does have 3 bonded pairs for a total of 3 electron groups. So if you kind of imagine a circle cut into 3 pieces, that angle of the circle would be 120 degrees. So that's the exact angle here for a trigonal planar molecule as well. So now we're going to draw ammonia, which is nitrogen bonded with 3 hydrogens. So nitrogen has 5 valence electrons, and hydrogen each has 1 for a total of 8. So we draw the molecule. We're going to put nitrogen in the center. I'm going to put hydrogen on each side, kind of around it. And then we have to draw our valence electrons. We know that hydrogen each has 1, and nitrogen's actually going to have 5. So when we drew our Lewis dot structure for nitrogen, we'd put 2 on one side and then 1 each on the other. So now we're going to go ahead and make our bonds connecting nitrogen to hydrogen. We're going to draw it like that. And now we notice that this is a little bit different than what we've drawn for the last few molecules because this does have lone pairs still remaining on nitrogen. So how many electron groups does nitrogen have in ammonia? So we've got an electron group for each single bond, but then this lone pair counts as an electron group too. So nitrogen has 4 electron groups. As we said previously, it does have one of those being a lone pair, so it's got 1 set of lone pairs. So now we're going to look and see what shape does ammonia make. It's got 4 electron groups, and one of those is a lone pair. So we're going to go down to the one here for 4 electron groups, and then we're going to find the ones that mark for 1 lone pair. So we're going to pull that down as well, and now our shape is going to be this one here, trigonal pyramidal. So trigonal pyramidal has the 1 lone pair and 3 bonded pairs, and looks similar to trigonal planar that we just looked at, but like it sounds, this one's going to make the shape kind of a pyramid. And why that is because the lone pair that's sitting there on top of nitrogen is going to push harder against those electron groups, those bonded pairs, than the bonded pairs will push against each other. So that lone pair on the top is going to force the rest of them to kind of push down, so it's no longer a flat molecule, it's instead a pyramidal shape. So these bond angles are going to be less than 109.5 degrees. And we can't give an exact number often when there are lone pairs involved because it can kind of fluctuate the exact amount that lone pair is pushing on the other bonded pairs. But our trigonal pyramidal is going to have 3 bonded pairs, so it still kind of looks like it has 3 electron groups, except that we have that lone pair. And so our lone pair is on the top, and that's what's pushing this molecule to make its shape. All right, now we're going to draw phosphorus pentachloride. So phosphorus has 5 valence electrons, and chlorine each have 7. So it's going to make a total of 40 valence electrons. So kind of like our models have been, we're going to put the one that there's just one of in the center. We're going to put phosphorus in the center. We're going to put our 5 chlorines kind of around it, looking almost like a starfish here. And then we're going to add our valence electrons. And we know chlorine has 7, so that means it's going to have most of its sides filled. Just one side's going to have 1 valence electron. And then for phosphorus, phosphorus is going to have 5 valence electrons. And so you'll kind of see what's about to happen because we've got 5 valence electrons for phosphorus, and there's 5 chlorines. Each of those have 1 unpaired electron. So we're just going to make a bond between that and its unpaired electron. So now we have 5 single bonds between our phosphorus and our chlorines for phosphorus pentachloride. So now we'll look at our molecular structure again to determine how many electron groups does phosphorus have. And so we're going to notice that each single bond is an electron group. So we have just 5 electron groups. All right, are any of these lone pairs? They are not. The only lone pairs we see are on chlorine. So we're specifically looking at phosphorus, and phosphorus has 0 lone pairs. All right, so we're going to now see what shape does this make with 5 electron groups and none of them being lone pairs. So we're going to follow on our left-hand column down to the one for 5 electron groups and then no lone pairs. We're going to follow that column down here, and it says that it is a trigonal bipyramidal shape. So trigonal bipyramidal looks like this. The trigonal part, the thing that looks like a triangle, is kind of there in the center, you can see. And that's pretty much the same shape as our trigonal planar was, except now we have 2 more bonded groups that make essentially like a north and a south pole here. So we have 2 different bond angles. That bond angle in the equatorial section is going to be 120 degrees between each of those bonded pairs. And then between the equatorial region and those ones that kind of look like they're at the north and south poles, that is going to be a right angle at 90 degrees. All right, let's draw another one. This is carbon dioxide. So carbon has 4 valence electrons. Oxygen each has 6 for a total of 16 valence electrons. We're going to put carbon in the center and oxygen around it. And carbon has 4 valence electrons, so we'll put its dots there. Oxygen has 6. And then we start to make our bonds between carbon and oxygen. And one thing to notice, after we've done that, this molecule looks a little bit different than the ones we've drawn previously because we still have some unshared electrons on both carbon and oxygen. So we're going to do a quick check of our octet rule. And we can see that oxygen has 1, 2, 3, 4, 5, 6, 7 over here. And this carbon has 1, 2, 3, 4, 5, 6 electrons it can use. So this is not following our octet rule. So we're not quite done with this molecule yet. We're going to need to make actually some double bonds. So we're going to take some of these electrons and we're going to move them around a bit. So this one from oxygen is going to come over here. This one from carbon is going to come right here. We're going to make another bond between carbon and oxygen. We're going to do the same thing on the other side. Move that electron. We're not moving it from one atom to the other, just kind of in a different spot because we've arbitrarily drawn those electrons on one side for our Lewis dot diagram. So now we're going to draw it like that. Now we've got carbon double bonding with two oxygens. So if we were to count our valence electrons on each, we see that carbon now does have 8, as does oxygen. So this is satisfying our octet rule. So now we'll look at our shape of carbon dioxide and answer how many electron groups does carbon have, that central atom. It's got one electron group here, this double bond, and one electron group here between oxygen. And this is where many students get a little tripped up because they'll think that that double bond is 2 electron groups. Even though it has double the electrons of a single bond, it still counts as 1 electron group. So carbon does indeed only have 2 electron groups on this molecule. Are any of these lone pairs? No, they are not. No lone pairs. We have lone pairs only on the oxygens, but right now this question is asking about carbon. So there are no lone pairs on carbon. So we're going to use our chart here again, and we're going to find the one that has 2 electron groups and then no lone pairs, and that's going to be linear. So linear, just like the name suggests, is going to be like a line, just a straight line here. So those 2 electron groups are going to try to be as far apart as possible, so that means they're going to be on opposite sides of the central atom, and our bond angle is going to be 180 degrees, just like a straight line. All right, now we're going to draw sulfur bonded with 6 fluorines. So sulfur has 6 valence electrons, fluorine each has 7. I think I'm realizing I only drew 5 there, so I actually need another one. So 7 times 6 is 42, plus another 6 makes 48 valence electrons. So as we draw this, we've got our sulfur in the center, we've got 6 fluorines around it, and each of those fluorines is going to have 7 valence electrons. So we draw them kind of in a way here where we have the one that's just by itself, the single electron, facing in, because we know that that's the one that's going to want to bond with sulfur. So then we add sulfur's 6 valence electrons, and we're going to create those bonds between sulfur and fluorine. So it kind of looks like this. I'm drawing kind of a little awkwardly. We'll see a better picture on the next side. So now we've got our sulfur hexafluoride, and how many electron groups does this one have? And it's going to have 6, one for each of the single bonds between it and fluorine, so 6 electron groups. Do we see any lone pairs on sulfur? We see some on fluorine, but not on sulfur, so 0 lone pairs for sulfur. Okay, so now what shape does sulfur hexafluoride make? We're going to follow down here for 6 electron groups, and then we'll find the one for 0 lone pairs, and it's going to be an octahedral. So an octahedral looks like this. It's got 6 bonded pairs, no lone pairs, for a total of 6 electron groups, and those electron groups are going to try to find the maximum separation, which is going to be creating angles of 90 degrees. So all of them will be exactly 90 degrees away from another electron group. So far we've mainly looked at the ones here in this column that don't have any lone pairs. To take a brief excursion, looked at trigonal pyramidal as well, but we've mainly looked at the ones with no lone pairs. So we're going to look at a few more that have more lone pairs. If you see drawings in your virtual textbook that have this kind of structure here with the lone pair, to me it kind of looks like an alien face. So you've got those 2 dots in the center that represent the electrons, and that thing around it is often shown to indicate that it is a lone pair. And don't worry about that. It's just really saying that that's the area where that lone pair exists. It's there on that nitrogen. So let's look at a few more examples with more lone pairs. Right, so sulfur dioxide. So sulfur is going to have 6 valence electrons, and oxygen each will have 6 as well. So that's a total of 18 valence electrons. And we looked at this one earlier at the start of class. We have sulfur with 2 oxygen. We'll add their valence electrons. And this one's going to be pretty similar to carbon dioxide. And you might be able to tell that right now because as soon as we make these single bonds, we still have extra electrons on oxygen. So what's going to happen is this lone pair from sulfur is going to actually kind of break up, and one electron will move over here and one over here. And then the oxygen electrons will come over here. And we're going to make a second bond between each of these. So this is our finished atom. We'll have a better picture again on the next slide without my drawings on it. Yep, so this is sulfur dioxide. It does have those 2 double bonds and 1 lone pair. So as far as our total number of electron groups, a double bond is 1 electron group and a lone pair is 1 electron group. So sulfur has 3 electron groups. So how many of those are lone pairs? We can see that sulfur has just 1 lone pair. Again, oxygen has some lone pairs, but for our molecular geometry, we're really just looking at the 1 central atom, so that is 1. So now what shape does sulfur dioxide make? It's got 3 electron groups and 1 lone pair. So we're going to find the one for 3 electron groups, and then we see 1 lone pair. It's going to create a bent shape. So sulfur dioxide is going to be bent. So when we had carbon dioxide, it was a straight line at 180 degrees, but now we've got that extra lone pair, and that extra lone pair does not want to be next to bonding pairs, so it's going to push those bonded pairs away from itself to create a bond angle of less than 120 degrees. So it's going to look like this, just a bent shape. I also wanted to show you that there are other bent shapes that have more lone pairs. So we looked at sulfur dioxide that had just 1 lone pair, but water also makes a bent shape, and water has 2 lone pairs. If we look at this with oxygen there in the center, it's bonded to each hydrogen, and then it's got the 2 lone pairs. So that's going to create another bent shape, but notice that this bond angle is significantly less than the last bond angle. So this bond angle is less than 109.5 degrees because that additional lone pair is now pushing against the other lone pair plus those bonded pairs to create an even smaller angle. All right, we're going to now draw a sulfur with 4 fluorines. So this is sulfur tetrafluoride. And sulfur has, again, 6 valence electrons. Fluorine each have 7. So that would be 34 electrons total. And we're going to draw our sulfur in the center, and then we're going to put our 4 fluorines around it. We're going to indicate the number of electrons. Our fluorines are almost full. They just have that one side that has a single electron that we know is probably going to bond with sulfur in just a second. And then sulfur, I'm going to put theirs in a different color. Sulfur has 6. So 6 valence electrons. So now we're going to start making our bonds here between sulfur and fluorine. And we'll notice that we have 2 electrons left over because sulfur has 6 electrons to bond, but it only needed to use 4. Fluorine doesn't have any electrons left that we could make any double bonds though. So those 2 electrons are just going to hang out on sulfur as a lone pair. So how many electron groups is sulfur going to have? We can see that there is 1 for each single bond, but then sulfur also had extra electrons that were a lone pair. So we actually have 5 electron groups. 5 electron groups, the 4 bonded and the 1 lone pair. So how many of these then were lone pairs on sulfur? It was just 1. Again, we have lone pairs on fluorine, but for our geometry, we're just looking at the ones on sulfur. So sulfur has 1 lone pair. So now we're going to look at what shape would sulfur tetrafluoride make. Remember, we have 5 electron groups total, and one of those is a lone pair. So we're going to follow down here to 5, and then find the one for one lone pair. And this one says sawhorse. So sawhorse is one name of it. I've also heard it as seesaw. That's what I'm generally going to call it. So seesaw or sawhorse kind of looks like this. The reason why I've called it seesaw is that it looks like a seesaw, like you would see at the playground. And it does have, again, one lone pair, 4 bonded pairs, for a total of 5 electron groups. That lone pair that's hanging out on the top, I'm going to draw where that would be up here, is going to push those bonded pairs away from the lone pair. So that's going to create that shape. So it's going to have a couple different bond angles. Along the equatorial, those are going to be less than 120 degrees, and the axial bond angles are going to be less than 90 degrees. So we've looked at a lot of different molecular shapes now. So the question that I had for students at this point was, what impact did the lone pairs have on the shape of the molecule? And so we kind of noticed in a lot of these is that those lone pairs really push those bonded pairs away even further than those bonded pairs would push themselves away. We could see that they really were acting very strongly on them, and that follows what we learned about the repulsion levels of those various electron groups. So just to review those electron group levels of repulsion, our most repulsive is lone pair to lone pair. So like in the water molecule we looked at, those lone pairs really don't want to be next to other lone pairs, so they're going to create even smaller angles when they're next to each other. Next up is lone pair to bonding pair. So not quite as repulsive as a lone pair to lone pair, but those lone pairs are still going to push those bonding pairs away pretty aggressively. And finally, a bonding pair to bonding pair. Even though those electrons still don't want to be next to each other, they're not quite as aggressively pushing apart as, say, a lone pair would. There's a few more examples that we didn't really get to in class. I just wanted to show you what those looked like. Square pyramidal would be if we had a total of 6 electron groups, on one of those being a lone pair. So 1 lone pair, 5 bonded pairs, 6 electron groups total. Those bond angles would be less than 90 degrees, and it would look like essentially a pyramid that its base is a square. So therefore we call it a square pyramidal. Another one is called T-shaped. T-shaped is going to have a total of 5 electron groups. Those 5 electron groups, though, are going to include 2 lone pairs. And in this molecule, those 2 lone pairs would really be kind of hanging out here above that central atom. And they'd be acting to push those bonded pairs into this T-shaped. And even though it looks like it's a 90-degree angle, it's actually going to be slightly less than a 90-degree angle. And then we've got square planar, which is 6 electron groups. Of those 6 electron groups, 2 are lone pairs, and then the rest are bonded pairs. So we have 2 pairs of lone electrons. They're going to essentially be on the bottom and the top of this to create this planar shape. So just like when we looked at trigonal planar, this is a flat shape. So it's flat, pretty much looks like a square. Its bond angle then is going to be exactly 90 degrees. 90 degrees between each of those remaining bonded pair electron groups. So in review, molecular geometry depends on 2 things. First, the number of electron groups around the central atom. And for that, we mean both bonds and lone pairs. So our total number of electron groups. Lone pairs. And then lastly, we want to know what that ratio is. So how many of those are bonded versus lone pairs? And so why are these shapes important? Here's 3 applications. Essentially, shape helps us determine our physical and chemical properties, such as boiling point. Shape can also help determine how molecules recognize and respond to each other. If you've taken biology, you've seen this is the case in regards to enzymes. Shape is also going to become more relevant once we start looking at chemical reactions, which is our next unit.